Hey guys, so this is going to be the first of two videos in section 2.4, which will be the last section that we do before your unit test. In this video, I want to introduce you to a new concept that's known as linear programming. And basically, in this video, we're going to be taking what we know about graphing systems of inequalities and doing our shading, and we're going to be adding just a little bit more to that. So let me start out by telling you what linear programming is. It's a method for finding a maximum or a minimum value of some quantity. And when you do linear programming, you're usually given a set of constraints. Okay, so today we're just going to be practicing with some straightforward examples, and in the next video you'll be looking at some applications of linear programming, how to apply that to business, profit, and some real-world scenarios. Let's start out with some new vocabulary for you. So the first vocabulary word I want you to know is what I mean by vertices. Vertices are going to be the points where our lines intersect. So today you're going to be doing several graphs, several lines on the same coordinate plane, and your vertices are the points where your lines intersect. There's also a vocab word I want you to know that's called the feasible region. The feasible region is going to be what we call the overlap area. So that's going to be the area when we do all of our shading, that's going to be the overlap of all of your shading. And then finally, this phrase objective function, that is a function that models the quantity you're trying to maximize or minimize. A function that models the quantity that you are trying to maximize or minimize. Remember what that term modeling means? We did some linear modeling in the last unit. Linear modeling, or modeling in general, is just a way of coming up with some sort of equation that represents what's going on in a real world situation. That's what that term models means. Okay, so let's go ahead and look at 1 and 2 here and just practice with some of the basics of this. Again, we're not going to be getting to anything too fancy until the next video. But all I want you to do in these two examples is you're given an objective function up here. Okay, so this is something I'm going to give you in these first two examples here. And what I want you to do is name the vertices of your feasible regions. Okay, and then I also want you to find the values of x and y that either maximize or minimize, and I'll tell you in each problem which one I want, this objective function. So for number 1, I want you to find the maximum for this function f of xy equals 6x plus 2y. So the way we do this is, first of all, we're going to locate our vertices of our feasible region. Okay, our feasible region is, again, this region that's outlined here, that's colored in. So if you imagine this is kind of a trapezoid shape, this region here would be our feasible region. Okay, everything that's colored in. And so what I want to do is I want to name the vertices of this feasible region. So that's just going to be the 4 corners of your trapezoid. We have 0, 0 here is one of my vertices. We have 6, 0 over here. We have 2, 4. And then finally we have 0, 4. Okay, so this trapezoid has 4 different corners, or 4 different points, and those are known as the vertices. Okay, now what we're going to do is we're going to plug in each of these xy values, each of these points, to our objective function. So we're going to plug in 0, 0 to the function 6x plus 2y, and then 6, 0, etc., and see what values we get as an output. Okay, so first of all, I'm going to find what f of 0, 0 is. And so to do that, I just need to plug in 0 for x and 0 for y. Well, when you plug in 0 for x and 0 for y, you get 0. Okay, now I'm going to find f of 6, 0. So that means I'm going to plug in 6 for x and 0 for y. So in this case, you get 6 times 6, which is 36, plus 0, so 36. Next, I'm going to plug in 2, 4. So 6 times 2 plus 2 times 4. That's going to give me 12 plus 8, which is 20. And lastly, I'm going to plug in my vertice 0, 4. So 6 times 0 plus 2 times 4, and that gives me 8. Okay, so now I basically have 4 different values because I had 4 vertices. So using the vertice 0, 0, you get 0. Using 36, or using 6, 0, you get 36. Down here 20, down here 8. And my job was to find the value that the vertice that maximizes this objective function. I wanted to find the maximum value. Well, that's just going to be the largest of your 4 output values, and the largest of these 4 output values is 36. This is my max. Okay, so to answer this question, my maximum is 36, that's the output, at my input was the 0.60. So I'm going to answer this question by listing what the maximum value is and which point or which vertice gives you that maximum value. That would be the 0.60. So for number 2 here, we're going to switch it up a bit, and this time we're going to find the minimum for this objective function, f of xy equals 4x plus y. So there's a little bit of a difference in this problem compared to the last one. And actually the first thing I want you to do is there is a little bit of a error here. I want you to get rid of this part down here, this shading. So on your paper, I believe there's shading down here. Get rid of all the shading that's below the x-axis for me. I don't want that to be there. So if you just want to make a note to yourself, there's no shading there, or there's not supposed to be anyway. That's the problem should just have shading up here. So I'll go ahead and outline that in blue. This is the only area I want there to be shading in. Okay, so if we go ahead and make the outline of our feasible region for this one, the outline is going to be, we have a boundary here on the y-axis, and then this line right here is another side to this figure, and then this third line here, and then the x-axis is kind of a fourth line. Okay, so if you think about corners again, we have a corner right here, okay, at the point 0, 5, so that's going to be one of our vertices. We have another corner right here at the point 2, 1, so that's going to be a second vertice. And then we finally have a point down, or a corner down here at the point 3, 0, so that's our third vertice. And that's going to be it in terms of the number of vertices. Don't assume that this point right here, okay, is a corner, because remember, this is just the end of the coordinate plane on the paper, but this region actually keeps going well off the paper. Okay, this is going to keep going forever and ever and ever. Okay, so really the only bounds or the only corners to this are these 3 vertices that I've highlighted. Okay, everything else, the region keeps going off the paper. So we're going to plug each of these 3 points into our function, just like we did the last one, except this time we're trying to find the minimum value. So I'm going to start with the point 0, 5. We plug a 0 in for x, we get 4 times 0, and then plus 5 if y is 5, and we just get the value of 5. Then I'm going to plug in the point 2, 1. So 4 times 2 plus 1, that would give us 8 plus 1, or 9. And then finally I'll plug in the point 3, 0. That would be 4 times 3 plus 0, which is 12. And so this time I want to find the minimum value. The minimum value for this problem is going to be 5 when we compare 5, 9, and 12. 5 is the smallest, so that means that our minimum is 5 at the point 0, 5. Okay, now let's go to the back side, and we're going to do a little bit more with this linear programming here. So for these examples here, I want a little bit more. The first thing you're going to do is you're actually going to construct the graph yourself. So you're going to practice graphing systems of inequalities again for examples 3 and 4, given the inequalities I've named here. You're going to name, again, the vertices, just like we did in the last problem, and you're going to find both the maximum and the minimum values this time. Okay, so similar to what we did for 1 and 2, just a little bit more for each problem. So the first thing I'm going to start out by doing is actually doing my graph, okay, constructing that. You're going to get your graph from these inequalities right here, okay. This function up here is your objective function, but that's not anything you're going to graph, okay. So this up here, just know that that's your objective function. You do not graph your objective function. You save that for the end, and that's what you plug your x and y values into. Okay, so this is just going to be like 2.3, the video that we just did for that, except instead of 2 lines, you're going to be doing 3, sometimes 4, maybe even 5 lines per coordinate plane. So the first line I'm going to draw is the inequality x is greater than or equal to 0. You should know by now that anytime you have x, not a y, that's going to be a vertical line. This one's going to be a solid vertical line, so I'll go ahead and I'll do that. Going to be a solid vertical line at x equals 0, so on the y-axis. Okay, and it's going to be shaded to the right, since it's a greater than. Okay, so that's my first inequality. My second inequality is y is greater than or equal to 0, so this one's just going to be a horizontal line on the x-axis, and for that one we'll shade above. Okay, my third and final inequality is x plus y is less than or equal to 8. So in slope-intercept form, that would be y is less than or equal to negative x plus 8. So that's going to have a y-intercept at 8 and a slope of negative 1. And that will be a solid line and we'll be shading below for that one. Really important to use a ruler on these since you also have to find intersection points. Okay, so it's really important to use a straight edge when you're doing these lines here. Okay, so now we're going to go ahead and we're going to find the overlap region, or our feasible region. That's going to be the area where just all of your shadings are crossing over. So again, we're going above the red line, to the right of the blue line, and below the purple line. So that's going to be this region right here, this little right triangle region. Here, that I'm going to color in green, that's going to be my feasible region. That's the overlap of all my shading. So my job is going to be to find the vertices of this region right here. Okay, what are the corners of this triangle, basically? Well, one of my vertices is going to be this point right here. That's the point 0, 8. So I'll go ahead and I'll list that. Another one is down here at the origin, so 0, 0. And my third is this point over here at 8, 0. Okay, so now I'm going to plug each of these points into my objective function, which is up here at the top. F of xy equals 3x plus 4y. So f of 0, 8, we'll do that one first. It's going to be equal to 3 times 0 plus 4 times 8. So that gives me 32. Okay, and then we'll go ahead and do f of 0, 0, which is just going to be 0. 3 times 0 plus 4 times 0 is 0. And then finally, f of 8, 0. Plug in a 3 for x and a 0 for y, and that gives you 24. Okay, so now we're going to be listing two values. We're going to be listing the maximum first. So comparing 32, 0, and 24, 32 is my maximum. So we'll say that the max is 32 at the point 0, 8. That's what gave us 32. And then for my minimum value is 0. So my minimum is 0 at the point 0, 0. Okay, finally number 4. We have the objective function f of xy equals 2x plus y, but again, we don't start there. We're going to start with our constraints down here, our 4 inequalities. So for this one, my first inequality is x is greater than or equal to negative 3. So that's going to be another vertical line on the x-intercept of negative 3, on the x value negative 3. So right here, shaded to the right. Okay, and then I also have another vertical line, x is less than or equal to 6. So that's going to be right here. And for this one, we're shading to the left. y is greater than or equal to 0. Again, that's going to be the x-axis. Shaded above. And then finally, we have the inequality x plus 3y is less than or equal to 24. So in slope-intercept form, you subtract x from both sides, you get 3y is less than or equal to negative x plus 24, and so y is less than or equal to negative 1/3 x plus 8. So this one will have a y-intercept at 8 and a slope of negative 1/3. Again, it's important to use a ruler when you're doing this so you can get your intersection points correct. Okay, so that's going to be this line right here. And for our shading for that one, we will be shading below. Okay, so again, you're looking for the crossover of all four areas, and I know with multiple lines it can get kind of messy, but again, just think it's to the right of my blue line, to the left of my red line, so that kind of constrains it to this window right here. You're above the x-axis, so above your purple line and below your green line, so you've got to be this little trapezoid region right here. So I'll go ahead and I'll color that here in yellow for you. This is my feasible region right here. So now again, the goal is just to find the corners of this region. There are going to be 4. You're going to have this point up here, which is negative 3, 9. So that's one of your vertices. You're going to have this point over here, which is negative 3, 0. And then if you go over to your red line, you've got the point 6, 6. And then down here, the point 6, 0. So 4 vertices for this one. Again, now we're going to plug into our objective function, f of xy equals 2x plus y, to find the max and the min. Why don't you pause the video and try this last part on your own, and then once you're done finding your max and min, click play to check your answers. Okay, so here's my work for plugging in each of these vertices to your objective function. So when you do this, you should get outputs of 3, negative 6, 18, and 12. That means your maximum is 18, and that's at the point 6, 6. Your minimum is negative 6, and that's at the point negative 3, 0. Okay, any questions you have on this video, feel free to write them down. Watch anything again that you need to, and once you're done with this video, you're welcome to watch the next video, which is going to be over applications of linear programming, so some word problems for that one. Until I see you next time, have a nice day. You're all wonderful people. Take care.